Howdy, students. Dan here. Um, just wanted to, sort of let you know. So there's no quiz today, and enjoy that. But there was a very good question sent in, so I wanted to address that. The question was, when do we use shells and when do we use washers, and sort of when does that matter, or how and why? And the extremely short answer to that is to make it easy. You just want to try to make it as easy as you can. And that just takes some practice on figuring out what to guess as to how to make that happen. Um, but as a teeny note on this, I personally have a little tirade about shells and washers, that I think that my, like, Dan's tip is to draw thickness. So what I mean by that is, if we took a typical washer, so a washer has an outer radius and an inner radius, and then it has a thickness. So that's how I sort of recommend drawing your washers. You can start here, you draw it symmetrically down, fill in the back sides, give it thickness. But then if I label all my dimensions, this is my inner radius, we'll say little r. This is my outer radius, we can call that big R. And my thickness, since my washer is vertical, my thickness is a change in the x direction, so I label it dx. And then if I need to figure out the volume of a washer, that volume is going to be, so how this works is it's the area, which the area is the outer circle. So this is pi outer circle squared inner, and then minus pi inner circle squared. So if we just rewrite that, we can do it. It works out nicely that way. So this is the area of the washer, this part of it here. And then we'd have to take the area times the thickness in order to get it. And then this sort of really answers the question. Once I decide how to draw the picture, if I want to integrate this over some values, my r's are integrated dx, so these need to be some function of x. If I were to have a washer this way, then its thickness would be that way. And this thickness is running vertically in the y direction, so I label it dy. And then if I were to integrate it, dy. So then these would need to be a function of y. Okay, so if you can draw in the picture, that question of which functions, or which way do I need my functions to be, like which variable should I use, is done that way. Real quick to draw shells. Shells have an outer radius and a height, and then they have a thickness, and that thickness I just sort of draw in on both sides, and you can kind of follow it around and connect them. So notice that thickness here is in the x direction. So this I would label dx. The height, I can label h. That often is, say, like our f of x, or an f of x minus g of x in these cases. And I have a radius, which our radius is often sort of x, because it's in the x direction here. I'd be measuring from the y-axis out a radius x. Okay. And then that lets me know if I'm going to integrate dx. Notice that those need to be functions of x. I can have a different type of shell. If I write my shell this way, it's got a little thickness to it. Note now that thickness runs in the y direction. So when my radius here, r, will probably just be something like y, or y minus something, because it's not reflected around the x-axis. And our height of it, h, is going to be essentially probably some f of y, or maybe an f of y minus a g of y. Okay, so that I hope helps a little bit with drawing thickness. So now, when would we use those? And like I said, the real trick is to make it easy. So if I had, say, a function that looked like this, and then I have another function that looks like that, and let's say we're going to reflect that around the y-axis. Well, if I'm going to reflect it around the y-axis, then if I were to go from this point to that point, then I could just figure out where these two functions are equal. We'll give these names. Let's call this g of x, and let's call this f of x. So in this particular case, I have a choice. I could use shells or washers, but if I use shells, then I'm going to be integrating this from this point to that point, and I just find those 2 points for where g of x equals f of x. And then I would draw in my shell. With a little bit of thickness. And we could integrate that. And my height of my shell, h in this case, is going to equal g minus f. G of x minus f of x. Okay, so that's cool. If I want to do it as washers. So what ends up happening is that I have to then break it into 3 different sections, because this point is lower than that point. So down here, if I draw a washer in, then I have this part of f minus that part of f. Check. So I just need to find those values. And then that works up until this line. And then from here to here in this section, my height is going to be this part of f minus g. And then up at the top, it's going to be this part of g minus this part of this part of g minus this part. outer minus inner. So if here's my line, outer minus inner. So you can see that in order to integrate this with washers, I'm going to have to integrate, we'll say that this has the height A, and we'll say this has the height B. So then I have to integrate some f of x minus, so I'm going to call this, oops, let's label this f of x1 minus f of x2. So this would be like x1 and this would be x2. So that's my height. And then I'd have to integrate that from finding this value here. We'll say that has height c. So then this would be the integral from c to a plus, and then I'm going to have to integrate from a to b plus the integral from b to, we'll give that top point, we'll say it's d. So if I want to do this with washers, I certainly can. I could just rewrite these functions as inverses, but then I have to do 3 different integrals, and that doesn't make it easier. So for this type of a problem, especially since they gave me the functions in terms of x, I want to do this one such that my integral ends up dx. So my thing has to have thickness in the x direction. So if that is my thickness and it gets rotated around, then you can see I've already had to just drawn a shell. So some ways, just looking at the picture told me, oh, I want to integrate this using a shell. A lot of the times it actually totally doesn't matter. If you were given, say, something like, integrate this where this is the function y equals x, and this is the function x equals 1. And we rotate that around the, say, x-axis. Well, then, sure. If I do it this way, I could do it with shells. Or I could totally do it with washers. It wouldn't matter. Just as easy. So, in some ways, which one you choose tells you which functions the variable has to be over. But in trying to, pick which one, try and make it easy. And some of it's looking at how the functions sort of break down and how the axis works and how these functions are given. If they give you, a function like, say, x squared minus 1 equals, let's say the square root of that equals y, then that's the top half of a circle. And maybe I tell you to rotate the top half of the circle around the x-axis. Then that's going to be much, much harder because I'm going to have to basically break it up as 2 different things if I try to solve this in terms of x, because I'm going to get x equals plus and minus y, y squared plus 1 square root. And I'm going to have to separate that at those 2 for this half of the integral and that half of the integral. So why would I do it that way when I can just leave it as a function of x, and then I know I want dx. What do I need to have in here? So if I want a dx, then this one would work out as being washers. Check. So whatever makes it easiest. Hope that helps. Have a good one. Enjoy not having a quiz. See you next week. Send me some questions.